I'm Gabriel, and this is part 2 of Physics and Stranger Things. This is the scene we created to represent Freefall from Stranger Things. Here is the scene that we were attempting to create. So for this scene, for Freefall, to find the displacement of how far Max fell, we need to make a key. So we know that acceleration is negative 9.81 meters per second squared. The time that she fell is 0.98 seconds, and her initial velocity was 0, since when she was at the top, she wasn't moving at all. So the equation we can use to find her displacement is the displacement formula. The displacement formula is V of O times delta t plus 1/2 A times delta t squared. When we plug all the numbers in from our key into the displacement formula, we get Max's displacement during this scene to be negative 4.7 meters. The next scene we picked represents Impulse in Stranger Things.
It wasn't supposed to end like this.
In this scene, Vecna is getting acted on by an impulse. To find this impulse, the first step is to make a key. We know that the mass of Vecna is 75 kilograms, his initial velocity in this scene is 0 meters per second, and he traveled approximately 4.8 meters in this scene. To travel those 4.8 meters, it took him approximately 1.89 seconds. To find the final velocity of Vecna during this scene, we can use the velocity formula, which is V equals displacement over t. So we do 4.8 divided by 1.9, and you get the final velocity to be 2.5 meters per second. After we do that, we can plug all of our values into the impulse formula, which is J equals mass times final velocity minus initial velocity. That would be J equals 75 kilograms times 2.5 meters per second minus 0 meters per second. Your impulse would then be 187.5 newtons west, but when we round to significant figures, that comes out to be 180 newtons west. So in this scene, Vecna is being acted on by an impulse of 180 newtons west. This next portion explains circular motion from a scene in Stranger Things.
I'm gonna talk about the keys from Stranger Things, which can be seen used in the following scene. Since this is based on circular motion, I'm mostly gonna focus on the spinning part of the thing. However, there aren't any measurements for it, so I had to compare it to whatever was closest to it. In order to find the radius of the thing, I had to compare it to the claws of a construction crane to find that it's 4 inches long, and then converted it to meters. Given that the claws go inward and that they seem to be pretty big, I assume that the radius that I found was just about half of one, which was the part that was going in, so making the circle. With that, I was able to find the mass of a regular claw, which was 114.4 kilograms, and then I calculated how long it took for one full circle to happen to find the period, which was 2.8 seconds. Using the formulas, you can get a velocity of 0.28, an acceleration of 0.77, and a force of 88.1.
The following portion represents projectile motion in a scene from Stranger Things.
In this scene, Lucas throws a Skittle into Max's mouth. This represents projectile motion. I first calculated the time the Skittle took to travel from Lucas's hand into Max's mouth. Then I found the range. I then solved for the final velocity and velocity impact of the skittle. The time it took for the skittle to travel from Lucas to Max was 0.59 seconds. The range between Lucas and Max was 18 meters. The final speed velocity of the skittle was 5.79 meters per second, and the velocity impact of the skittle was 30.6 meters per second.
The following portion represents friction in a scene from Stranger Things.
In this scene, Steve and Robin are seen driving away from the Demogorgon. The bumpy and broken roads causes them to slow down due to the friction. The variables needed to calculate the force of friction are the coefficient of friction and the normal force. In this scene, the coefficient of friction is 0.5 and the normal force is 2,000. To calculate the force of friction, you multiply the coefficient of friction and the normal force. When you multiply 0.5 and 2,000, you get a force of friction of 1,000 newtons.
The following portion represents forces in a scene from Stranger Things.
Oh my god, oh my god, oh my god, oh my god, oh my god.
Nothing! Feels heavy!
Yeah, Lucas, they're on us.
Where are you?
Cornwallis.
Amen, Elman, Jerry!
Copy, Elman.
To find the forces while Dustin is riding his bike in this scene, the first step is to make a key. So, the values we already know is that Dustin weighs 65 kilograms. The gravity on Earth is negative 9.81 meters per second squared. And we can find out the coefficient of friction by looking at our reference table. Since Dustin is riding his bike, which has rubber tires, on concrete, the coefficient of friction will be 0.68. To find the force of gravity, we can do 65 kilograms times negative 9.81 meters per second squared to give you a force of gravity of negative 638 newtons. To find the normal force, we can multiply negative 1 times the force of gravity, which would give you a normal force of 638 newtons, which is the opposite. To find the applied force, we can do mass times acceleration, which would be 65 kilograms times 2.29 meters per second squared, which would give you an applied force of 149 newtons. To find the force of friction, we multiply the coefficient of friction by the normal force, which would be negative 0.68 times 638 newtons. This would give you a force of friction of negative 434 newtons. The final force we have to find is F net, which is all of the forces combined. To find this, you do force of gravity plus the normal force plus the force of friction plus the force applied. The F net would be negative 285 newtons, which shows why Dustin is slowing down while riding his bike in the scene, which is why he has to constantly pedal to maintain his speed.